Good afternoon, class. We are looking at pre-calculus practice test number 2, module 2, chapters 3 and 4. Here's chapter 3, polynomial and rational functions, the second. All right, let f of x be x over x minus 2, which is a rational function. Sketch the graph of f using technology to determine whether f is a one-to-one function. At this point, we have seen how to graph functions, and we've gone through the process. Remember, if you have a rational function, you know how to come up with the vertical asymptote, horizontal asymptote, slant asymptote, the rest of the stuff. So over here, we are going to assume everybody knows that, and that's why the technology is mentioned here. So you graph this, and notice this is a one-to-one function. It passes the HLT, horizontal line test. So what you do, you start finding the inverse function. And of course, if f is a one-to-one function, find f inverse and sketch a graph of f inverse. So what we do is that, first of all, f of x, we're going to change the name to y because it makes it easier to work. Number one. Number two, we're going to interchange x and y. So this becomes x, this becomes y. Right here, we have found the inverse. However, we are going to solve for y. To do so, we do the cross product. So x times y minus 2, 1 times y. So x times y minus 2 becomes xy minus 2x. Y times 1 becomes y. Because you're solving for y, you are going to move this way and making it into negative y, this one to the other side, making it into 2x. And you factor the y out from the left side, you get y times x minus 1. We are going to divide by x minus 1, and we're going to give it a name f inverse. So y, or f inverse of x, is 2x over x minus 1. We graph this again, we are using technology, and the function is one-to-one, so is its inverse. So notice VA's, vertical asymptotes, and HA's, horizontal asymptotes. What do we notice? Well, this is the vertical asymptote, or x equals 2 for this one. This is the horizontal asymptote, or y equals 2 for the other one. This is a horizontal asymptote if you look at this one, because they have the same degree, namely 1. The coefficient of the top over the coefficient of the bottom becomes y equals 1. So here's the vertical, here's the horizontal asymptote, and notice x equals 2 corresponds to y equals 2, and y equals 1 corresponds to x equals 1, because the two functions are inverse of each other. So that's one of the properties. As far as the domain is concerned, clearly this one x can't be 2. Everything else is fine. So domain for the original function f is all real numbers except 2, meaning negative infinity to 2, union 2 to infinity. Again, notice if you set this one equal to 0, x becomes 2, and the domain is all except that. And domain becomes range, everybody, for the other function. So the range for f inverse is the same thing. So the range of f inverse is the same thing, because if two functions are inverse of each other, domain of one becomes range of the other. What about domain of f inverse? Take a look at this one. You said the denominator equal to 0, x minus 1 equal to 0, x becomes 1, so you exclude 1. All real numbers except 1. So you write from negative infinity to 1, union 1 to infinity. Again, just to make sure we get that, this one, x minus 1 equal to 0, x equals 1, must be excluded to give us the domain of f inverse, which is the same as the range of f, minus infinity to 1, union 1 to infinity. So I hope it's clear to everybody. Solve the following inequality, graph the solution set, and write the solution set in interval notation, x squared minus 3x minus 18 over x plus 2 greater than or equal to 0. Well, there are several ways of doing that, everybody. And one way is to graph the entire function, this function. But you definitely don't want to go that route. That's way too long. So the best course of action is to make sure the top and the bottom are both in factored form. If you look at the top, since this is x squared, you want two numbers. The product is negative 18. The sum is negative 3. So you get positive 3 and negative 6. And now that it's in factored form, you set the top 0, the bottom 0, and they become your critical points that you got to pay attention to. So if you set the numerator equal to 0, okay, the numerator n of x is 0. That means x is negative 3, x is positive 6. If you set the denominator equal to 0, that means x is minus 2. So you put those three numbers on a number line in order from smallest to largest. So x goes from negative to positive infinity. When x is negative 3, this expression is 0. When it's negative 2 is UD undefined. When it's positive 6 is 0. The next step is to figure out where this function is positive, where this function is negative, and so on. So you pick up, this is a number line, and we are going to go with the following technique. TP, short for test points. So you pick a number here, for example, negative 4. Here, negative 2.5. Here, let's say 0. And here's, let's say, 7. Now, one thing that happens, because each one of them has exponent 1 or odd for that matter, if you find one of them, the rest of them alternate. But in any event, let's put negative 4, and it's easier to put it in this format. So take a look at what happens. If I put negative 4 here, so let me erase this one. I want to make a point here. If I put negative 4 here, so this becomes, and I'm interested in sign, negative 4 and 3 is negative 1. Over here becomes negative 10. Over here becomes negative 2. So negative times negative divided by negative is negative. I'm interested in sign, and the rest of them alternate. So negative, positive, negative, positive. But if you want to check, one easy part to check would be 0 between these two numbers. If you put 0 here, if I put 0 here, I get positive. negative, positive. Positive times negative over positive is negative. See that? You can do the same with the rest of the numbers. Or just as I mentioned, the reason they will alternate is because each one has exponent. So we go back to this, and we want to write this where it's positive. So that means positive here, positive here. So what do we do? The interval notation is from -3 to -2, union 6 to 8, to infinity. At -3 is 0 and equality is fine, but at -2 is undefined, it's parentheses. At 6, it's 0, it's bracket, and of course, infinity is always parentheses. So pay attention to the way you write this, everybody. One more time. Positive from -3 to -2. -2, because the function is undefined, you go with the parentheses. Union 6, bracket, because it makes it 0 to infinity. Now, before I continue, I want to make one more point. Well, let's actually show it on this one. It's on a number line. It's easy to see that it goes from 6 to infinity. Solid point means it's included. And in between -3 and -2, -3 takes a solid point, -2 takes a whole. What I want to add is this. Even if we had a product, let me erase everything. If we had x plus 3 times x minus 6 times x plus 2 larger than or equal to 0, we would use basically the same sign graph. And everything is the same. The only difference is because it doesn't have a restriction, this becomes a bracket. So this thing changes for this one. -3 to -2, both of them take brackets. Union 6 to infinity. So that would be the difference, and I hope everybody's following. The end behavior of a polynomial function is the behavior of the graph of f of x as x approaches positive infinity or negative infinity. The degree and the leading coefficient of a polynomial function determine the end behavior of the graph. F of x equals a sub n, x to the power of n, plus a sub n minus 1, x to the power of n minus 1, all the way to a sub 0. They ultimately look like the leading term, which is a sub n, x to the power of n. So take a look. If the degree is even, like to the power of 2 or 4 or 10,000, even. And if the leading coefficient, a sub n is the leading coefficient. So in this case, that means a sub n. That means a sub n. Positive, negative. So it looks like x squared. And if it's negative, looks like minus x squared. So in this case, x goes to infinity, so does y. In this case, x goes to negative infinity, y goes to positive infinity. That's the meaning of f of x approaches positive infinity and x approaches negative infinity, and they approach infinity, and this is the other way. If the leading coefficient is positive, but the degree is odd, looks like y equals x cubed. And if it's negative, looks like y equals minus x cubed. Those are known as the end behavior. In the case of a y equals x cubed or f of x equals x cubed, if x goes to negative infinity, so does y. If x goes to positive infinity, so does y. This one is the other way around. X goes to positive infinity, y goes to negative infinity, and vice versa. So those are known as the end behavior, and that will help with the graph. Also, we have behavior near and x-intercept theorem. Behavior near is 0. Multiplicity of 0 is x minus c to the power of m. So m is considered the multiplicity. If m is odd, f crosses the x-axis at c0. If it's even, it can't cross at the x-axis. So as you can see, this is the x-intercept. Okay, it crosses. In this case, the multiplicity is 2. Can't cross. In this case, the multiplicity is 3. Both of these odd numbers, they cross. What's the difference, however? The higher the multiplicity, the flatter the curve is at 0. The sum of the multiplicities is the degree of the polynomial function. Also, number of zero theorem. A function defined by a polynomial of degree n has at most n distinct, unique, complex zeros. Let me write this a plus bi. Okay, there are how many of them? N of them. And remember, the multiplicity means, for example, if it repeats, if you have x minus c to the power of m, m counts as m number of zeros. It's just being repeated, okay? So we're going to graph the following polynomial using the end behavior and behavior near and x-intercept. So uh, I'm going to put this in a format that it's easy to see. First, notice this is the uh, leading term, so it looks like y equals x cubed. So the first and the third quadrant, so that we should know. Okay. The next thing is that if we could put this in factor form, it makes it easier to see the intercepts as well as the multiplicity of that and how that works. If we put these two together, we can take x squared out. And these two, we're going to take -1. The reason we do that, so it creates a common factor of x minus 5. So x minus 5 times whatever is left. What is left from here? X squared. What is left from here? -1. And as you know, x squared minus 1 is x minus 1, x plus 1, or x plus 1 minus 1 in any order. And so notice this one has exponent 1. No exponent means exponent 1. Same thing here, same thing here. So all of them have multiplicity equal to 1. As the exponent is 3, there must be 3 zeros, and there are. This one, 5, 0, -1, 0, 1, 0. So set this one equal to 0. Set this one equal to 0. So there are 3 x-intercepts. So this is 5, 0, 1, 0, -1, 0. So we have 3 x-intercepts. The y-intercept is easier to go to the original one and see if x is 0, you get 5. Okay, so the y-intercept is 0, 5. And because the leading term is x cubed, n is odd, more specifically, n equals 3. And a sub n, which is 1, is positive. So the end behavior looks like y equals x cubed, which basically means the end behavior will give us the first and the third quadrant. I hope everybody is following that. It's very straightforward, everybody. So in other words, what it means as x goes to negative infinity, as as x goes to negative infinity, f of x goes to negative infinity, as x goes to infinity, f of x goes to infinity, that means the first and the third quadrant. And so, and because all have multiplicity 1 or odd, when we hit those, it crosses, then it comes back up, crosses, and it looks like this. And this is even a better graph, everybody. So pretty straightforward. So knowledge of the end behavior, which depends on the leading term, and the x-intercept, which depends on the multiplicity, will help us graph. All we have to do, the end behavior, a few intercepts, and we are done. We're going to do the same thing, graph the following polynomial using the end behavior and behavior near an x-intercept. G of x is x minus 2 squared times 2x plus 3. So first, let's look at the x-intercepts. This one gives us 2, 0, set that equal to 0. This one gives us negative 3 halves, 0. I hope everybody can see that this one has multiplicity 2, this has multiplicity 1. So 2, 0, set this equal to 0, 2, 0. What is the multiplicity? 2. This one set it equal to 0, negative 3 halves, 0. What is the multiplicity? Well, there is no exponent. That means exponent is 1. Which means those 2 points, they will cross at those 2 points. So here's one of them, 2, 0. Here's negative 3 halves, negative 1.5. This is negative 1. This is negative 2 in between. So the graph will cross. Let's also find the x-intercept, the y-intercept. So if I put 0 here, if I put 0 here and 0 here, I get negative 2 squared times 3. Negative 2 squared, 4 times 3 is 12. And I get, by the way, we use this notation in calculus, meaning it can't cross that because the multiplicity is even, and that's your y-intercept. So what happens, the end behavior, of course, please notice this is x squared and the rest is not important. So x squared times 2x is 2x cubed, and it continues indefinitely. I'm interested in the leading term. The leading term is 2x cubed. So ultimately, the end behavior, the first and the third quadrant, looks like x cubed. So n is odd, meaning 3, and a sub n equals 2 or positive. That's important to understand, everybody, okay? So the end behavior is very straightforward, meaning x goes to negative infinity, so does y. Remember, f of x is the same as y. X goes to positive infinity, so does y or f of x. And so the graph, starting from here, as we hit this point, we can't cross. Why not? The multiplicity is 2. So it has to bounce back up and goes through this point and that point. And there you have it. Now, where does the local max occurs? This is the information we will find out in calculus. There is a way to find it, okay? And of course, this is a much better graph. It's easier to see the intercepts, the end behavior. And so we are done with that. Very straightforward, everybody. What is the least possible degree of the polynomial? Write an equation for the polynomial graph. So here's the graph given. What is the least possible degree? Should be 4. Why is that? Look at peaks and valleys, the number of terms. This is 1. This is the second one. This is the third one. We have 3 terms. So you have n, which is larger than that, at least 5. Okay. So the theorem says that whatever the degree of the polynomial is, the number of terms is at least 1 less. Or on the other hand, however, the number of terms, the degree must be at least 1 more. So number of terms plus at least 1 more, that would be your degree. All right. Now, we want to write an equation for that. Well, we can write y or f of x equals some number times this one minus 3, that means x plus 3. This one is minus 2, that means x plus 2. This is positive 1, that means x minus 1. And notice it crosses here, but it bounces back. In other words, look at this 3 and look at the multiplicity must be 2 because it bounces. Actually, here is my work again. And so a, or some number like 8 times x plus 3 times x plus 2 times x minus 1, but this one is x minus 1 squared. Okay, because the multiplicity is squared. Now, ya, because we don't know what is the leading coefficient. How do you get that? Well, look up one more point, an easy point. What would be the easiest point? The y-intercept located at 0, 3, which means replace the x with 0 and y or f of x with 3. When we do that, this becomes 3, this becomes 2, this becomes minus 1, and this is 3. Minus 1 squared is positive 1. So you have 6a, and so a is 3 over 6, or 1/2, and you put it in. F of x is 1/2 x plus 3 times x minus 1 squared times x plus 2. Of course, in any order you put it is fine. Find the degree, leading coefficient, and the maximum number of real zeros of the polynomial f of x is 2 plus 3x to the power of 6 plus 4x to the power of 7 minus 6x. Also describe the end behavior or long run behavior. To be able to answer that, the very first thing you want to do, you want to put this in descending order. So 4x to the power of 7 is first, 3x to the power of 6 is second, this is third, and this is last. So put it in descending order first. When you have the descending order, the very first term is your leading term. The degree is 7, the leading coefficient is 4. So find the degree, leading coefficient, maximum number of zeros, n equals 7. That would be the degree. The maximum number of zeros is always the degree. The end behavior. Well, the end behavior follows the leading term. Or x to the power of 7. N equals 7, which is odd. A sub n, which is 4, is positive. So it behaves like x cubed. In other words, as x goes to negative infinity, f of x of y goes to negative infinity. As x goes to positive infinity, f of x or y goes to positive infinity. That's the meaning of it. Use number of zeros theorem and Descartes' rule of sign to discuss real zeros of f of x. Fill up the table. F of x is 3x to the power of 7 minus 4x to the power of 4 plus 3x cubed plus 2x squared minus x minus 3. So what is Descartes' rule of sign? Descartes' rule of sign determines the number of positive and negative zeros. Let f of x be the polynomial function f of x equals a sub n, x to the power of n, all the way to a sub 0, with terms in descending powers of x. The number of positive real zeros either equals the number of variation in sign occurring in the coefficient of p of x, or is less than the number of variation by a positive even integer. What do we mean by that? So let me show you the meaning of part A first, and then we go to part B. This one is 3x to the power of 7. Just look at the sign, positive, negative, positive, positive, negative, negative. So according to this, the number of positive real zeros either equals the number of variation in sign occurring in the coefficient of p of x, or is less than it. So as you can see, from positive we go to negative here. So let the leading term is 3x to the power of 7. N equals 7, so M maximum number is 7. So this is 7, everybody. That's the first thing. So maximum number of zeros. Then positive to negative, there is one change. Negative to positive, there is another change. Positive to positive, there is no change. Positive to negative, there is another change, and there is no change. So we have 1, 2, 3 changes, which means positive real zeros must be 3. Part B, the number of negative real zeros either equals the number of variation in sign occurring in the coefficient of p of minus x, or is less than the number of variation by a positive even integer. So first thing first, we have to calculate f of minus x according to this. So what is f of minus x? This becomes 3 minus x to the power of 7, which is minus 3x to the power of 7. Because x is to the power of 4, x or minus x makes no difference, so this is the same. This one, because it's cube, it becomes minus. This one, because this is exponent to it, remains unchanged. This one is plus x, this one is minus. So this is f of minus x. I'm assuming no one has any problem evaluating f of minus x. So look at the sign changes. So this goes from negative to negative, no change. Negative to negative, no change. Negative to positive is one change. So negative, 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 positive, positive. So we have one change here. There is no change, positive to positive, and there is one change here. So we have 1 and 2 changes. So positive real zeros, there were 3 changes. Negative must be 2. This is what Descartes' rule of sign says. Also, if the total is 7, then what are the rest? Imaginary zeros. That means the form of a plus bi. That's the meaning of it, everybody. And so 3 plus 2 is 5. What is missing? 2. So there must be 2 imaginary zeros. So that's up to here. And then when it says or is less than the number of variation by a positive even integer. What does that mean? That means this can be 3, or it goes down by 2, becomes 1, and then it can't go negative. This can go down to 0. So if this is 1, because you go down by 2, you get 1. This one is 0, then you must have how many here to make up number 7? So 3 goes down by 2 becomes 1. 2 goes down by 2 becomes 0. 1 and 0 adds up to 1. So we need 6 more zeros to make up 7. That's how this thing works, everybody. This is the Descartes' rule of signs.